Have you ever wondered what's going on inside a self-driving car's brain? Or how your phone can magically find every single picture of your dog out of thousands? Well, it all comes down to something called computer vision. Today, we're going to pull back the curtain and show you exactly how a computer learns to see. And it all starts with one fundamental, kind of mind-bending difference between how we see the world and how a machine does.
So the big, ambitious goal of this entire field is right here on the screen. We want a machine to look at a scene, just like this one, and not just see it, but to actually understand it. To know, hey, that's a building, that's grass, that's the sky. To get what it's looking at. For you and me, that's instant. It's totally effortless. We don't even think about it. But for a computer, this is one of the most profound challenges researchers have ever tackled. So what's the big disconnect? What makes something so incredibly simple for us so monumentally difficult for a machine? And this right here is the whole problem in a nutshell. On the left, that's what we see, a rich, detailed photograph. But on the right, that's what the computer gets, a cold, raw grid of numbers. That's it. It has no idea what a building or a sky is. It just has a long, long list of numerical values that, for now, mean absolutely nothing. It turns out this giant chasm between the numbers on the right and the meaning on the left actually has a name. It's called the semantic gap. And bridging this gap, that's the entire game in computer vision. It's all about teaching a machine how to translate that meaningless grid of numbers into a rich, meaningful concept, just like we do. So how in the world do we start building that bridge? Well, we have to get our hands dirty and really understand what an image is to the machine. And we're going to do that by looking at some really simple code that peels back the layers of a single picture to see what's really going on under the hood. All right, let's meet our test subject. To us, it's obviously a dog, right? I mean, it's pixelated, sure, but our brains just fill in the gaps instantly. To the computer, though, this is just a file. It has no idea it's looking at an animal. It's just a chunk of data. So the first thing we can do is just ask the computer to describe this data for us. We can use a super simple line of code to ask it, hey, what is the shape of this image file? What are its dimensions? And this is what it spits back, a set of three numbers, 32, 32, 3. Now, this might look like total gibberish, but believe it or not, this is the complete DNA of our dog image. It's everything the computer knows about its structure, all packed into three little numbers. Let's break that down. The first number, 32, tells us the image is 32 pixels tall. The second number, 32, tells us it's 32 pixels wide. And that last number, the 3, that's the really crucial part. It means that for every single one of those pixels, there are three numbers that describe its color. One for red, one for green, and one for blue. Okay, so now we kind of get the whole grid. But let's zoom in even further. Let's focus on the story of just one of those tiny little dots that makes up the entire picture. And this is it. This is the big aha moment for understanding computer vision. A digital image is nothing more and nothing less than a giant grid of numbers. That's all it is. Every pixel is just a coordinate in that grid with three numbers that tell it exactly what color to be. Okay, so if that's true, if it's really all just numbers, then we should be able to change the image just by changing the numbers, right? Let's test it. With this line of code, we're going to find the pixel at row 10, column 16, and we're going to manually change its red, green, and blue values to 255. That's the maximum value, which should create pure white. And boom, there it is. Look closely. By changing just three little numbers in that massive grid of data, we've placed a single white dot right on the dog's head. This is direct proof. We are literally manipulating the image by doing math. All right, this is where it gets really, really powerful. I mean, changing one pixel is cool and all, but what happens when we apply some simple math to all the numbers at the exact same time? Let's see. In this first example, we're taking every single red, green, and blue value in the entire picture and doing one simple thing, dividing it by 2. And look at the result. The whole image just gets darker. All the relationships between the pixels are the same. It's still a dog, but their overall intensity has been cut in half. That is a huge global change from one simple line of math. So what about something that looks way more complicated, like rotation? Well, fundamentally, it's just shuffling numbers around. Think of it like a Sudoku puzzle. We're just telling the computer, hey, take the color value that was in the top left corner and move it over to the top right corner. And then do that for every single pixel. We're not even changing the colors, just their addresses in the grid.
And here is the real kicker. Every advanced computer vision task you can possibly imagine. I'm talking about an AI generating photorealistic art, a security system recognizing a face, a medical scan identifying a tumor. It all boils down to this one fundamental principle: performing mathematical operations on enormous grids of numbers. So we've cracked the code. We've seen that, to a computer, sight isn't really about understanding, it's about mathematics. And that completely transforms our whole perspective. The question is no longer, can we make a computer see? We know the answer is yes. The real question, the one we have to think about for the future, is, now that we understand how it sees, what do we want to teach it to look for?